Greetings, fellow cosmic explorers. Today, we embark on a captivating journey to unravel the mysteries of the origin of the universe. Throughout history, brilliant minds have proposed various theories, each offering a unique perspective. Join me as we dive into the chronology of these theories and examine their pros and cons. But first, let's begin with the most renowned theory, the Big Bang. The Big Bang is a scientific theory that explains how the universe began. According to this theory, the universe started as an extremely hot and dense point called a singularity, about 13.8 billion years ago. At this singularity, all matter, energy, space, and time were compressed into a tiny, infinitely small point. Then, something incredible happened. The singularity started to rapidly expand, and the universe began to expand with it. It's important to note that the Big Bang was not an explosion in space, but rather an expansion of space itself. Imagine inflating a balloon. The dots on the surface of the balloon move away from each other as the balloon expands. As the universe expanded, it also cooled down. The intense heat of the early universe gradually decreased, allowing atoms to form. Initially, there were only simple particles like protons, neutrons, and electrons. Over time, these particles came together to form atoms, which are the building blocks of matter. About 380,000 years after the Big Bang, the universe had cooled enough for light to travel freely. Before this time, the universe was filled with a dense, hot plasma that prevented light from moving freely. This event is called the cosmic microwave background radiation, and it is like a snapshot of the early universe. As the universe continued to expand, gravity started to pull matter together, forming galaxies, stars, and planets over billions of years. The stars produced heavy elements through nuclear reactions, and when they eventually exploded as supernovae, these elements were scattered into space. This is how the ingredients for planets, including Earth, were formed. The Big Bang theory is supported by a lot of scientific evidence, such as the observed redshift of distant galaxies, the abundance of light elements in the universe, and the cosmic microwave background radiation I mentioned earlier. However, there are still many questions that scientists are trying to answer, such as what happened before the Big Bang and what caused the initial singularity. To resolve the singularity problem, scientists propose the inflation theory, which suggests that the universe experienced a period of exponential expansion shortly after the Big Bang. This rapid expansion explains the uniformity of the cosmic microwave background radiation and the large-scale structure of the universe. This rapid expansion had profound implications. It smoothed out irregularities, making the universe remarkably homogeneous and isotropic on large scales. Tiny quantum fluctuations in the inflation field were stretched across vast distances, laying the seeds for the structure of the universe we observe today. The inflation theory provides elegant explanations for several key features of our universe. It resolves the horizon problem by explaining how regions of the universe that were never in direct contact can have similar properties. Additionally, it accounts for the observed uniformity of the cosmic microwave background radiation, the afterglow of the Big Bang. While the inflation theory has compelling strengths, it also faces challenges. One of these challenges lies in the lack of a concrete understanding of the inflation field itself. Scientists continue to explore potential candidates for this mysterious field and investigate its properties. To further validate the inflation theory, scientists conduct experiments to scrutinize the cosmic microwave background radiation, searching for specific patterns that would support the predictions of inflation. Additionally, ongoing observations of the distribution of galaxies and cosmic structures provide valuable insights into the validity of the theory. The inflation theory elegantly accounts for the observed patterns in the universe, such as the absence of magnetic monopoles. However, it requires precise fine-tuning of initial conditions, raising questions about its own origin and the underlying mechanism driving the inflation. The multiverse theory is a speculative concept in physics and cosmology that suggests the existence of multiple universes or a multiverse. According to this theory, our universe may be just one of many universes that exist, each with its own set of physical laws, constants, and conditions. There are different variations of the multiverse theory, The first one is called the Level 1 Multiverse Theory. This is the simplest form of the multiverse theory and is based on the idea of cosmic inflation. According to this theory, shortly after the Big Bang, the universe underwent a rapid expansion known as cosmic inflation. During this inflationary period, different regions of space expanded at different rates, leading to the formation of separate bubble universes. Each bubble universe may have its own distinct properties, making them effectively separate universes. Next, we have the Level 2 Multiverse Theory. This variation of the multiverse theory is based on the concept of an infinite or eternal universe. In an infinitely large or eternal universe, any event that can happen will happen an infinite number of times. This means that there are an infinite number of regions within the universe that have conditions suitable for the formation of galaxies, stars, and even life. In this view, each of these regions represents a separate universe within the multiverse. The final multiverse theory is the Level 3 multiverse. The Level 3 multiverse concept is based on the branch of physics known as string theory. String theory suggests that there are more than 3 dimensions of space and that our universe may be one of many brins, short for membranes, floating in a higher dimensional space called the bulk. Each brin could correspond to a different universe with its own set of physical laws and particles. It's important to note that the multiverse theory is still highly speculative, and there is currently no direct observational evidence to confirm its existence. However, scientists explore these ideas as potential explanations for some of the fundamental questions in cosmology, such as the fine-tuning of physical constants, the nature of dark energy, and the origin of our universe. However, the multiverse theory opens up fascinating possibilities and challenges to our understanding of the cosmos. It is a subject of ongoing research and debate among physicists and cosmologists, and future observations and experiments may provide more insights into the validity of the multiverse theory. The final theory to describe the origin of universe is the string theory. String theory is a theoretical framework in physics that aims to describe the fundamental building blocks of the universe and the interactions between them. It suggests that the fundamental particles we observe, such as electrons and quarks, are not point-like particles but tiny, vibrating strings of energy. These strings can vibrate in different ways, and the different vibrational modes give rise to different particle properties, such as mass and charge. One of the key motivations behind string theory is its potential to unify all known fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces. Currently, our understanding of the universe is described by 2 separate theories: general relativity, which explains gravity on a large scale, and the standard model of particle physics, which describes the other 3 forces and particle interactions. However, these theories are incompatible and cannot fully explain phenomena at the smallest scales or the origin of the universe. In string theory, the fundamental entities are strings, and their vibrations determine the properties of particles and forces. By incorporating gravity into this framework, string theory provides a consistent mathematical description that could potentially unify all the forces in a single framework. This is often referred to as a theory of everything or a unified theory. According to some versions of string theory, the universe we inhabit could have originated from a process called cosmic inflation. Inflation is a period of rapid expansion that occurred shortly after the Big Bang. It is believed that during inflation, quantum fluctuations in the early universe could have given rise to the variations in energy density that eventually led to the formation of galaxies and other cosmic structures. String theory provides a potential framework to study the physics of the very early universe, including the processes that may have triggered inflation. By analyzing the dynamics of strings and their interactions, researchers aim to understand the fundamental nature of space, time, and the laws of physics at the earliest moments of the universe. It's important to note that string theory is a highly complex and mathematically challenging area of research. It is still an ongoing field of study, and many aspects of the theory are yet to be fully understood and tested. Experimental verification of string theory predictions remains a significant challenge, and researchers continue to explore new avenues and develop mathematical tools to advance our understanding of the theory and its implications for the origin and nature of the universe. As we conclude this cosmic voyage, remember that the quest to understand the origin of the universe continues. Science continually pushes the boundaries of knowledge, unraveling the mysteries that surround us. Join us in our exploration as we uncover the secrets of the cosmos, one discovery at a time. Thank you for joining us today. Until our next cosmic adventure, keep looking up and keep questioning. Stay curious.